So welcome back to my next Modern Java by Example webinar. Today we're going to look at a really interesting topic related to the use of sequential and parallel streams in order to process and create the contents in a recursively structured object that will hold the contents of a recursively structured directory. And we looked at this a little bit yesterday in the context of the fork join framework, but today we're going to revisit it and look at some really cool things that involve the use of custom spliterators and custom collectors for Java sequential and parallel streams. It turns out at the moment, apparently GitHub is down, so I can't show you the repository that way, but I'll point you to where to find all the code here in just a moment. So let's go ahead and start. I will share my screen and we'll be off to the races here. Okay, so first and foremost, whoops, don't want to leave this meeting. Let's go ahead here and go over to my account at Vanderbilt. Go here. This is the Modern Java by Example webinar site. And if you take a look here, this is today. And this is where the link is at GitHub. So as soon as GitHub comes back up again, please feel free to go to this page and click on that link and you'll find all the code that we're about to talk about. So let's now go over to my IntelliJ folder, and we'll jump right in. So what we're going to do here is we're going to take a look at the recursively structured directory hierarchy, which basically is this. This is just a whole pile of files. These are all the files that I have in my live lessons repository that are source code and project-related files. And so as you can see, there's quite a number of them here. There's something like 2,200 documents and folders and subfolders in this hierarchy. So it's a lot of material to parse. And what we're going to do basically is we're going to go ahead and snarf this all up and put it into a recursively structured object, which we're going to call a folder. And the folder, of course, will contain subfolders and documents going all the way down for all the different contents of the directory structure here. And then we're going to do a bunch of operations to process that content. So you can kind of think of this as the sort of thing you would do if you were building a DOM tree for doing some kind of XML parsing where you read everything in and then make a tree that you could use to query and search and do other kinds of operations to. So that's the big picture of what we're going to do here. So now let's go ahead and take a look at the actual code. So I put everything into a file folder called works. That's where we've got all the content rooted, and we'll see how we get to that in a second. Here's the main program. The first thing we're going to do is parse the command line arguments, and I'll talk a little bit later about what you can do on the command line. Right now, we're not using any command line arguments. We then warm up the thread pool. We then go ahead and run all the interesting tests sequentially first. We're going to use a really cool technique to be able to switch back and forth between sequential streams and parallel streams. And then we're going to go ahead and run all the same tests again in parallel. So let's go ahead and do that just so you can see what the output's going to be. So here we are, we're running the program, and you can see that we first warm up the thread pool, and then we go ahead and run all the tests sequentially, and it goes and figures out sequentially using a sequential stream that there's 2,200 entries in this rooted folder that starts in my works directory. There are 222,105 lines in there, and then we go and look for all uses of the word completable future, and there's 822 of them. Then we go ahead and run everything in parallel. Of course, we get the same results, but now let's take a look and see what the difference in performance is. And it's kind of funny because if you run these programs a couple different times, you'll get somewhat different results. So let's run it again just for kicks and see what results we get this time. So basically, most of the time, the parallel stuff works faster, which is really not a big surprise. This particular computer I'm working on it's a Macintosh MacBook Pro that has 16 gigabytes of memory, and it's got 4 cores, which are hyper-threaded. So it's basically got essentially 8 virtual cores. And you can see here that for some of the operations like counting the entries, the difference between parallel and sequential is pretty insignificant. When we start doing things like counting the number of lines, searching, creating the folders, and so on, those things tend to run quite a bit faster using parallel operations than sequential ones. And that's pretty much what we'd expect. We'd expect that parallel processing would speed up. But it's nice to see these kinds of improvements because it demonstrates the point I'll make in a minute. The difference between the sequential version of the code and the parallel version is basically non-existent. They're almost identical, but we can get a nice speed up by going to parallel processing. Keep in mind that there's also a lot of disk I/O here because we have to read everything off the disk and put it into memory, and then we work on it in memory. My particular computer has a large amount of SSD disks, so disk operations are fairly fast as well. Okay, so with that, let's go ahead and take a look here at run tests. So you can see that we're going to pass in a Boolean that will dictate whether these tests run in parallel or sequentially, and you'll see a clever technique I use in a second to make this work. Then the next thing you can do, you can see we go ahead and going to call the create folder test. We'll look at that in a second. And then we run that and time it. We then do the count entries test, which goes ahead and figures out how many items there are in the folder. We then go ahead and do the count lines test, which figures out how many lines there are in the contents of this folder. And then the final thing we do is we do the search folders test, which goes and looks for the word completable future in all my examples. So basically, all of the things we're doing here are based on the folder that we create here in the create folder operation. So we get a folder that's the result of this, and then we use that for everything else. So we put an in-memory data structure that contains the contents of the recursively structured folder, the directory, and then we do things with it. Okay, so let's go down and take a look first at create folder. This is what kind of kicks things off. And what we're going to do here is we're going to use a little helper method called test data factory get root folder, and we give it the name of the folder, and then we also go ahead and say whether we want this to run in parallel or not. And you'll see that this is handled in a very clever and cool way throughout all the code. So let's go ahead and follow this. So if you look at the get root folder, you can see it goes to the folders class, and it uses a factory method called from directory. And what that's going to do basically is it's going to go ahead and treat what we gave this as a directory, and then it's going to go ahead and populate the object with the contents of that directory. So let's go ahead and take a look here at from directory. So from directory is part of the folder class, and the folder class is basically something that's called a durant. So if you go look at durant, you can see that this is the durant class, and it's an abstract class that keeps track of directory entries that could either be folders or documents, or subfolders or directories or subdirectories and files. That's the way to think about that. And so it's just an abstract class, and then we have a document class that extends it, and we have a folder class that extends it. And it basically keeps track of the path, keeps track of the contents of the document when it's a document, keeps track of the size, and then it has a bunch of basically setters and getters that do various things. So that's kind of just the core of everything. And then we have the folder class that extends this, and this is, of course, meant to store the subfolders and documents recursively throughout our hierarchy. The way we do that is we have a list of durants, which we call subfolders, and we have a list of durants, which we call documents, and depending on the structure, those will either have contents or not. Here's the constructor. We go ahead and initialize the subfolders and documents fields to be empty arrays, and we pass the path up to the superclass. Then there's just a couple of helper methods that we use to get those particular fields, so we don't have to expose the representation directly. That's just good object-oriented design. Now things start to get a little more interesting. So far, it's just been basically sort of setter-getter style methods. Now let's take a look at something cool. So one of the things you're going to see here is once we populated our folder, we're then going to go ahead and do a bunch of streams operations on it. In order to do that, we have to be able to convert the contents of the folder into a stream. And the way we do that is through the stream method, which of course comes out of the box with all the containers, all the collections you have in Java, like array list and hash map and so on. So we're just following that pattern. We have stream and parallel stream. And you'll see that both stream and parallel stream are little wrappers for the stream support.stream method. And stream support.stream takes a spliterator and a flag to indicate whether it should make a sequential stream if the flag is false, or a parallel stream if the flag is true. And the spliterator, of course, is this spliterator here. This is the spliterator that we use to take the contents of this particular folder, this particular entry, let's say it's the root folder, for example, and then create a stream. And it uses the spliterator to split the contents of this folder up into chunks. And there's two different spliterators. One is a recursive spliterator, and one is a batch spliterator. We're going to focus on the batch spliterator here, and then we'll come back later if we have time, and we're going to go and talk about the batch folder spliterator. Looks like my internet is doing something a little flaky. Let's see if I can figure out. Oh, I think it's back. Okay, good. If you guys are having any problems hearing me, feel free to comment or chat, and I will see what I can do to change that. Okay, so now what we've got here is we're going to look at the batch folder spliterator later. That's going to be used to break up the contents of this into individual chunks. Looking down a little bit more in folder, we get the from directory file, and that's the one that we had called back over here. So get root folder ends up calling from directory, and that's in the folder class. And if we go to from directory, then you can see what we're about to look at. This is really cool code, what we're about to see here. So what we're going to do at a high level is we're going to go ahead and start with the root path, which will be the entry point into our works directory. And then we're going to go ahead and we're going to use the files walk method. And files walk, we actually looked at files walk yesterday when we talked about the fork join pool. Files walk is going to take a path, and it's going to give us a stream back that will give us all the contents in that top level of the folder. So yesterday we used the version of walk, which just walked the entire recursive structure. This time we're going to use a slightly different technique where we're going to bound it to just one level at a time. And you'll see why we're going to do that as we look at this in a minute. So we're going to go ahead and get basically a stream to the contents of the topmost folder initially. And notice we have a stream, and also you'll notice we use this cool exception utils rethrow function helper method. And what this does is it converts something that is a checked exception, like all the annoying IO operations in Java. It turns it into something that can be used as a non-checked exception, or a runtime exception. And it's just a clever little adapter to do that. And I do that on purpose because I don't like to litter my code with try-catch blocks, especially for the stupid checked exceptions. And I also don't like to end up having to put the exception, the throw clauses into the method signatures. That's just so annoying, and it makes streams so much more complicated. So I use this clever little adapter to make everything work without having to deal with checked exceptions. So then we take that stream, and notice that nothing has happened to this point because we haven't hit a terminal operation. Then we go ahead and apply that function, which will go ahead and walk through the folder at that level, that one level. And this will give us back a path stream. Again, nothing has happened yet. It's still all lazy evaluation. And here's why we do this lazily. If the parallel flag is set, the parameter that was passed in, then we go ahead and convert this stream, which by default is a sequential stream, into a parallel stream. So we're now going to have a parallel stream if we've set the flag. And that way we can keep our code identical and then enable and disable parallelism as a flag. What we do then is we go ahead and we take that stream, which is now either a parallel stream or a sequential stream, and we do two things to it. First, we're going to use the filter operation to basically ignore ourselves so we don't have a recursive loop here. So we ignore this path as we're doing this. And then the next thing we do is we go ahead and collect everything into a, we use the folder collector to collect the contents of the stream into a folder. So what we're going to do here is we're going to make a folder here, passing in the flag, indicating whether we're doing this in parallel or not, and then also passing in the root path. And that's given to the two-folder factory method, which will make us a folder collector. We're going to go look at the folder collector in a second. But at a high level, what we're doing is we're taking the stream of subfolders and documents at this level in our traversal, and we're going to collect them into a folder. Now, not surprising, this is all going to be done recursively in a very clever way, as you'll see in a second. So let's go ahead and follow ourselves down. Here's two-folder. Two-folder goes ahead and makes a new folder collector, passing in the parallel flag in the path. So let's go take a look at folder collector. So here's folder collector. You can see it just goes ahead and stashes these parameters away in local fields. So what is a collector? Well, or what is folder collector? A folder collector is a collector that's parameterized with three types. One is the path. And so we're going to have a stream of paths that we're going to be collecting. We're going to collect this into a folder, and we're going to return the folder as the result of the operation. So let's take a look and see what the collector does. Collectors have basically 5 key methods that they have to implement. They're factory methods. So one of them is the supplier, and this is used by the streams framework to return a supplier that, when called, will make the appropriate mutable result container, which in this case is a folder. And this folder that we're going to make will be connected to the path that was passed in. So this folder will know that it's rooted at that path. And you can see we return a supplier. So when the streams framework needs to create our folder for the collector, it'll say basically supplier.get, and that will trigger the creation of the folder. So that's our mutable result container. We also have to define an accumulator, which is a factory method that returns a by consumer. And what the by consumer in this case will do is it'll take the folder that we've been accumulating into and the latest entry in the stream, and it goes ahead and adds that entry to the folder using either parallel or sequential processing. So that's why we stash away that field, so we can use that to dictate what's going to happen. So that's what Accumulator is going to do. It's going to return a by consumer that the streams framework will use to collect the stream entries into the folder we created by the supplier up here. Then there's also another method called combiner. Combiner is only used for parallel streams, never for sequential streams. And what it does is it takes two subresults, in this case two folders, two subfolders, and it merges them back together again. And we're going to come back and talk about what add entry does in a second, and we're going to talk about what merge does in a second. Those are really important methods to understand to see how the wonderful recursive nature of this program actually unfolds. And then the last thing we're going to talk about, or there's one more thing, but this is the main other thing, is the finisher. The finisher method gets called after everything has been accumulated. And what that's going to do is that's going to go ahead and take the folder that we've accumulated into, compute its size, because now we've got it full of all of its subfolders and documents, so we figure out the size of it, and then we return that folder as the result of collect. So collect will return this folder that now contains all of those contents. There's also a method called characteristics that basically it's a factory method that gets the characteristics of the collector, which in this case will just be, we don't care about the order that things happen. Okay, so that's basically a high-level view of the collector, of the folder collector. The most important thing to note here initially is, what is this add entry doing? And you're going to see in a second what it does. It's really cool. What add entry does is, this is a method defined in the folder class that takes a new entry from the stream and goes ahead and inserts it into the folder. So what it does, and this is really neat, this is where all the recursion comes from. If the entry is a directory, then we're going to go ahead and recursively call the from directory method again, but on this entry. Remember, this is the one that was basically in the list of, in the stream of elements that was in the initial folder. So now we're going to go ahead and recursively and synchronously go ahead and read that entry, which is of course basically a directory name or a subdirectory name, a path name, into the hierarchy that was underneath the top level folder we just processed. And when that comes back, then of course we're going to go ahead and add that to our subfolders list. In contrast, if what we saw was not a directory, but was instead a document, we're just going to go ahead and do the from path method for a document. So let's go ahead and talk about what the from path method is for the document. So here's document from path. First of all, what's a document? A document is a durant. So this is basically the composite pattern. Document is a durant, and it has the from path method, which takes a path to a file, and it creates this helpful little exception adapter. And the purpose of this is to basically make it easier to use checked exceptions. This is really cool. So this is going to be a function version of these. And what it's going to do is it's going to go ahead and call the read all bytes method on the files class, get the bytes of this file, store it into the document, and then it goes ahead and returns a new document. And that document, of course, encapsulates the contents and the path. So that's what it means to get a document. You would read the document in and store it in a document object. It means what it means to get a file. So let's go ahead and pop back to where we came from. So when we're all done here, we're going to go ahead and actually, I don't actually have to do this anymore. So let's go ahead and zap that because that's handled through other means. So that's what it means to add an entry. And you can see that what's happening here, we're starting at the root of our folder, and then we're going to go ahead and make a stream of all the contents there. And then we turn around and call the collector, and the collector goes through every element in the stream, looking at each one to see whether or not each entry, each element is a directory or a file. And then it will go ahead and do the appropriate thing here, adding the document into the documents list, adding the subfolder, if there's a subfolder, into the subfolders list, and then recursively calling from directory on the folder to populate it. So it's basically building this thing sort of top down by each entry. So it's essentially doing a breadth first search, I think. Maybe it's a depth first search. I think it's doing a breadth first search of the contents and then populating the elements and building it up as it goes. Okay, so that's what add entry does. Let's take a quick look at what merge does. Merge is called for the parallel streams case, and what merge does is it goes ahead and it takes all the contents in the item we're merging from, all the subfolders, and we add it to the end of our current subfolder. And then we take all the documents from the folder we're copying from and we merge it into our documents. We then go ahead and set the new size, and then we return the folder that we're doing. So this is basically how we're merging things together. Okay, and then there's also another method here called compute size, and this is called at the very end of all the processing in order to be able to update the count of the number of subfolders and documents in this particular folder. So that's how we know how many elements there are in the folder. Okay, so now let's kind of pop back a few levels here. And that's what the accumulator did, and that's what the merge method does. So hopefully that kind of helps to clarify what is going on in this particular situation. Okay, so now let's pop back out of this. We've looked at the collector, and the collector is what we used in order to set all the wheels in motion. And here we are back to where we started. So we walked through everything at the topmost root. We got all the elements in a stream, and we collected stuff. And when we collect things, that goes and triggers all of the processing to take place at that point. So that the collector that we create triggers all the recursive processing. So what we end up with when all is said and done is we're going to end up with a durant that points to a folder that contains all the contents of the entire directory structure that we looked at. Okay, so that's what create folder does. So once we've got ourselves a folder, then we can start doing the other operations. So let's go take a look quickly at what those other operations were. And that'll take us back here a little bit, popping out. And let's go back to the main program. So you'll notice the first thing we did is we got ourselves a folder and we timed how long it took to run that. And then we went ahead and we counted the number of entries in the folder, we counted the number of lines in the folder, and we searched for words in the folder in either doing it in parallel or doing it sequentially. So let's go ahead and take a look at count entries first. So count entries, keep in mind we've got ourselves a root folder that's a durant. It's a folder that contains all the contents that we read in from the file recursively. And now we're going to say root folder.stream. And this stream call is going to trigger the spliterator to take the contents of our folder, which we read into memory, and then turn it into a stream. And we'll look at that in a second. And then, of course, depending on whether we set the flag to parallel or not, we'll get a parallel stream or a sequential stream. And then we simply turn around and we count the number of elements in the stream. So count is a terminal operation that will use the stream in order to return the count of the number of entries in the folder. So let's go take a look real quickly at the stream method. And you can see that the stream method here calls stream support.stream. And this, of course, will be initially a sequential stream, and then we can toggle it using the technique I showed you back here to make it either parallel or not. But let's go back here for a second. So this is going to end up calling the spliterator method. And here's the spliterator method. And we're either going to be using the recursive spliterator or the batch spliterator. I'm going to start by talking about the batch spliterator because it's a lot easier to understand. The recursive spliterator is very, very cool, but it's more complicated. So here's the batch folder spliterator. Batch folder spliterator is going to use basically a reverse breadth first search to go through the contents of our folder and then visit every one of the nodes. And basically, in this particular case, it'll go ahead and either do a try advance or a try split followed by try advances. And we'll talk about that in a second. There's some really good videos that talk about spliterators on my website, and I'll give you some links to that in just a minute. So batch folder spliterator is an abstract spliterator, so a lot of the things are filled in automatically. We keep track of the batch size. You'll see how that gets used in a second. And then we use an iterator. And we're going to use an iterator to be able to iterate through the durant, through the folder, recursively one element at a time in a very clever way using reverse breadth first search. Here's the batch folder spliterator. We give it the folder we want to work on. It goes ahead and computes the initial batch size, which is basically the size of the folder divided by the number of available cores, just for kicks to start off with. And then we go ahead and we initialize our breadth first search iterator. And that's the thing we're going to iterate over. We'll look at the breadth first search iterator in a second, but first let me show you the methods we have in the spliterator that use the breadth first search iterator. So down here we have a try advance method. The try advance method is going to be called under certain circumstances. If you're using a sequential stream, then it's used to walk through every element in the folder, one element at a time. If you're using a parallel stream, it's used when you reach a point where you don't want to do anything else in parallel, when you don't want to split things any further. And we'll take a look at that in just a second. So let's assume, for sake of argument, we're doing a sequential stream. So what we're going to do here is we're going to say, is there anything in our iterator? If the answer is yes, we're going to take the next item in the iterator, which is basically the next durant in our folder, and we're going to go ahead and accept it. So that's going to be a way to pass it back to the streams framework. So action.accept is a consumer, and that will then pass the next element back to the streams framework where it can be converted into a stream and processed further by other streams operations. If there was something in the iterator, we return true to say, hey, streams framework, keep going. But if there wasn't, we return false saying, okay, we're done. There's no more entries to process. So try advance basically combines has next and next. So it does it in one method that basically has an out parameter and returns a Boolean, as opposed to requiring has next and next for iterators. But we can use has next and next in our implementation. Let's now go ahead and take a look at the try split method. If there's anything left in the iterator, we go ahead and call a helper method called split batch, which you'll see what that does in a second. Otherwise, we return null. Whenever null is returned, it said, okay, I'm done trying to split streams framework. Now go ahead and call try advanced to do all the rest of the processing on the elements that you've got. Here's split batch. Split batch works very much like the linked list spliterator. If you take a look at Java collections linked list, they have a spliterator, and it works kind of along these lines. They start off by allocating an array of objects of m batch size, and you'll see that we're going to double this each time through. Every time we need it, we're going to double it. And that's just to try to grow over time. And then what we're going to do is we're going to iterate while the index that starts at 0 is less than the batch size, and iterator has next is returning true. In other words, we still have things in our iterator. We're going to go ahead and store the next element in the iterator into the dirent array and increment the index by 1. So we're basically copying the contents of these elements into this array. And when we're done, we're then going to use the factory method on spliterator, called spliterator, which takes the dirent array and the size, the index, and it goes ahead and it returns a spliterator. So that's basically a Java helper method that's defined. You can go look at it if you want to. You can see what it does is it basically uses array spliterator on this particular array. So it will use the array spliterator to split it up a little bit further. So that's how we're going to get spliterators back from this thing. The next question, what's the breadth first search iterator? So the breadth first search iterator is a class that's an iterator. It implements the iterator interface, and it iterates over durants. And we are going to use reverse breadth first search. You'll see what that means in a second. So we keep track of the current entry to process if there is one, and then we keep track of the folders and the documents we're processing. And here's what the constructor does. The constructor takes the root folder, makes it the initial first element, and then it takes any subfolders and any documents reachable directly from the root folder and sticks them into the folders list and the docs list, respectively. So everything's got initialized now. Has next is going to check to see if there's anything left that we haven't looked at already in our breadth first search iteration. And if the iterator, if the current entry is null, then we do some stuff. Otherwise, if the current entry is not null, we're going to do something else. We'll take a look at that in a second. So if the current entry is null, that means we don't have a current entry, in which case we're going to go ahead and do a few little magical things. And what we're going to do here, notice that when we started out that the current entry is not null. And so the first thing we're going to do is we're going to return the current entry as the entry to begin with. Let's take a look. If the current entry is null, however, then we're going to come in here and check to see if there are any subfolders that are left to process. If we've not processed any of our subfolders, then in that particular case, we're going to go ahead and remove the last subfolder. That's why this is reverse breadth first search. So we are going to have the set of folders or subfolders we've got. We're going to take the last one and remove it, and that shrinks the list by 1. And then we're going to go ahead and we're going to make that the current entry. And then we're going to go ahead and take all the subfolders in that folder and throw them into the folders list. And we're going to take all the documents from that folder and throw them in to the documents list. So now we've populated this stuff with some more things. And then if there are, so if there were no folders, we're going to check to see if there's any documents. So if there were documents left, then we're going to go ahead and make the current entry the last document in the documents list. So again, reverse breadth first search. That shrinks the item by 1. And so when we're all done with this, we're going to have a current entry or not. So of course, initially, if you take a look up here, we started out with the root folder. So we do have an entry. So this whole thing is just going to return true. And then that will call the next method. And what happens now is the next method will take the current entry. That's what we're going to return. And then it sets the current entry to null. and returns what the original current entry was. And so this is how we start our whole breadth first search going. And so what it's doing here is basically doing reverse breadth first search through the folder hierarchy that's rooted in the root folder, and it's returning those things, and then try advance is going through one at a time and converting them into elements that will go into the stream. So that's the batch folder splitterator. And it's pretty straightforward to understand. It's basically doing reverse breadth first search and converting that into streams. Okay, so let's go back over to the main program. So what happened there was we created a stream of these durants. We either run it in parallel or not, and then we count the number of elements in the stream. Pretty straightforward. Let's go take a look at the other operation here, the next one in line. This is count lines. So let's go ahead and take a look at count lines. Count lines, if you run this program, you can see takes longer to run. And the reason why is it actually has to touch the contents. And so here's what we're going to do. We're going to, once again, create a stream, which triggers our folder splitterator. We make that a parallel stream or not. And then we go ahead and do the following. We're going to go ahead and take that stream, and we're going to filter it so we only want to process documents. And here's what isDocument is. It's just a little predicate method that sees if the durant is an instance of document. If it is, then it's going to be the, it's going to return true. So obviously it doesn't make any sense to count the number of lines in a directory or a folder. So we're going to count the number of lines of documents. So we take the stream, we filter out all the documents, or we filter the documents so we have them. And then for each document, we're going to call a really cool helper method called split as stream. And it's going to take the contents of the document, and then it's going to go ahead and split it around new lines. So let's go ahead and take a look at split as stream. Split as stream is a little helper method I defined here that takes the regular expression, which in this case is new line, compiles that into a pattern, and then it uses the split as stream method to split the document according to the new lines. So what we're going to end up here with is a stream of lines where, because we split it on the new line. By the way, there's undoubtedly faster ways to do this. I'm just having fun with streams to illustrate how all this works. So what we're doing here is we're creating a stream of lines, and then we're going to count the number of lines in each document, and then map to long will convert that into a stream of counts, where each count in the stream is the count of the number of lines in each of the documents that was passed as the input to map to long. So we just go ahead and we sum all those things up. That ends up in line count, and then we go ahead and print line count with the number of lines. All right, that's pretty cool. Now let's go ahead and take a look at the next operation. This is search folders. So search folders is going to take the folder and the search word we're looking for, and it's going to go ahead and search it either in parallel or sequentially. So here's search folders. Now again, there's undoubtedly faster ways to do this, but I just wanted to show off some really cool parallel streams techniques here. So what we do is we take our root folder, convert it into a stream, make that stream either a parallel stream or a sequential stream. We filter out everything that's not a document. We only want documents. And then for each document, we're going to call this helper function called Occurrences Count, where we're going to give it the contents of the document, the word to search for, and whether we want the search to take place in parallel or not. And we'll look at Occurrences Count in a second, but you can imagine that'll return a count for each document, and then we're going to sum up that count, and then that'll get printed. So let's go ahead and take a look at Occurrences Count now. So Occurrences Count is going to take a document and a search word, and it splits the document up into words. And again, this is not the fastest way to search things, but I'm just having lots of fun with stream features to show how you could use streams. And it also demonstrates the use of parallel streams nicely. So we're going to use that same split as stream helper method we did before, except rather than splitting it by new lines, as we had earlier, we're now going to split it into words. So we have a stream of words. And then we can decide to process that stream of words sequentially or in parallel. And then what we do is we go ahead and we filter only the words that match the search word that we're looking for. So search word here, if search word equals the word in the stream, then it gets through the filter and we'll end up counting it. So we're basically going to do a count of the number of times the search word appeared in the stream. So once again, having way too much fun with streams and stream features. So that's basically kind of how the program works at a high level. I kind of now have walked through it. What I'll do right now is take some questions, and then we'll go ahead and, if we have time left, we might have some time, we'll see if we can take a look at the recursive spliterator, because that's pretty cool. So let me go ahead and go down here, and let's take a look at the questions. Why do we pass a Boolean parameter to folder collector? The reason for doing that is because we want to recursively pass that down to all the calls that we make to folder or durant. Let's see, what is it? I guess it's durant from directory. We want to be able to do durant from directly, and we want to conditionally make that parallel or not. So that whole thing has to be passed down because the folder collector needs to recursively make calls to add entry on the folder, and then add entry needs to recursively be able to call down to from directory. And so you need to be able to pass that flag through, otherwise it'll be inconsistent in terms of whether we use sequential or parallel. Returning this without synchronization will not be a problem. I assume that you're referring to the part of the program that was the merge method. There's a merge method in folder, and I was returning this. That's perfectly fine because the way that this particular collector works is it's a non-concurrent collector. And non-concurrent collectors, when used with sequential streams, are trivially not going to have any race conditions. Non-concurrent collectors, when used with parallel streams, also have no race conditions because the merging is done in one thread, even though the processing takes place in a pool of threads. So that's very cool. In the case of parallel streams, each thread creates one instance of breadth first search iterator. So let's see, that you're talking about the spliterator there. I don't think so. No, the spliterator doesn't run in parallel. The spliterator works in such a way that it'll work properly. Let me rephrase that. Splitterators do not have to worry about race conditions. You never have to put locks in your splitterators because the way they work is the splitteration at any given point takes place in only one thread of control, and the result that comes back will then go ahead and be processed in other ways. So we have one instance of the breadth first search iterator, but when the splitterator is used for parallel, then we're going to end up with those things being used in a slightly different way. In one of the APIs, are you passing this as an argument? You'll have to point me to which one you're talking about. So this code, as you can see, works perfectly fine for both parallel and sequential processing. Let's see. In the case of parallel stream, is the reverse breadth first search actually doing the traversal in reverse order? It'll be doing traversal in the reverse order at that level. So at any given point, it's at the level that you're working at in the traversal. Iterators by design are supposed to be accessed in a single thread only. That's correct. There is nothing, as I just said, the way that splitterators work is you never have to worry about putting locks in your splitterators. And our splitterators are being used with iterators to implement them. So of course, those iterators are also not going to have to worry about being accessed concurrently. So there's no problems here with race conditions at all. Okay, if you can find me the example you were referring to before having to do with passing this, I'll be happy to take a look. Okay, so we have a few minutes left. Let's go ahead and reshare the screen and go back here to this part. Probably wouldn't be a bad idea to go over to the batch folder spliterator for a second. Let's see here. Yeah, so in this particular case, we should be fine. I don't think we have a problem. Okay, let's take a look at the recursive folder spliterator. So in the recursive folder spliterator, what we're going to have is something more complicated. It's actually a lot more complicated than what we had in the other example. And so what we're going to do here is we're going to keep track of the current folder like we did before. We're going to keep track of the list of folders, subfolders, and documents to process. Those will also be managed properly. The constructor goes ahead and initializes the folders list and the docs list as we did before. And we start out by adding the folder to the folders list. So that's where everything starts from. And then you'll see there's this internal spliterator that we use to split things up when we need to for the recursion. The try advanced method is similar to what we had before, but it tries to be a little bit more clever. What it's going to do is it's going to go ahead and see if there's any documents. And if there are, we're going to go ahead and remove the document in reverse breadth first order at that level. Then we're going to go ahead and take a look at the folders list and see. So if there are no documents, we're going to then see if there's any folders, subfolders. If there are, we'll remove the last subfolder at the end of the list. And then we go ahead and once we make that the current entry, we take all of its contents and we throw it into the folders list. And we take all the contents of the documents and throw them into the documents list. If there's no documents, if there's no folders left, then we return false because we're done. And then the last thing we do if we don't return false is we accept the current entry. So that's kind of how we start. We accept the current entry. Here's try split. Try split is what's more complicated. Unlike the previous approach, which used the spliterator factor method that's on the spliterator's interface, which basically uses an array list, as you saw before. What we're going to do in this particular case is we're going to be more clever. We're going to try to recursively split things in half wherever possible, particularly with respect to folders. So if we have a folder with a bunch of subfolders, then we're going to see if the number of subfolders in that folder is greater than or equal to 2. And if so, we're going to split it into 2 halves and then recursively process each of the halves. And here's what it looks like. So we're going to go ahead and do the folders list size to get the size. Then we split the folders. If the size is greater than or equal to 2, we split the folders. If the size equals 1, we have a single folder. So we're going to basically take its contents and then we'll split those things up. And if finally we only have documents and if we only have documents, then we're going to go ahead and handle that. So let's take a look first at the entry where we have multiple folders. So here you can see what we're going to do is we're going to go ahead and break up our search space, our spliterator space, into 2 chunks. One chunk will be what we call the left-hand folders, and that's everything in the current folder from 0 up to the split pause. And then we're going to go ahead and update the right-hand side, which is us, to take the split pause up to the end of the folders list. So that'll become the new folders list. So now we've got 2 sublists. We have everything from 0 to split pause, which is right in the middle, and from split pause to the end. And then, so we've modified ourselves, and then we go ahead and create a new reverse folder spliterator, which will cover the left-hand side of things. And so in that particular case, we're going to pass in the left-hand folders and the new array list, which will be initially empty, and then it'll go ahead and start the processing there. So that's where we try to split the folders in half. Then we have another case here where we have a single folder. So if we have a single folder, we go ahead and remove it from the folders list. And then we go ahead and take all the documents that we've got and we put those into the documents list. And then we go ahead and make all the subfolders from the current folder. So we kind of move all of its contents that it holds up a level. And then if we've got no folders left, we call split current folder and docs, which handles the documents, as we'll see. Otherwise, we go ahead and make a new recursive folder spliterator to work on the subfolders. So we kind of hoist those things up and then go ahead and do the recursive partitioning. Again, we're trying to find a way to balance these things more evenly. And this works particularly well if you have large directories with lots of documents and subfolders in them, because then you can really get parallel processing to work in your favor. And then the final method here is split current folder and docs. If there's no folder at all, we're done, and everything else gets done by try advance. The elements, for example, the documents, for example. Otherwise, we go ahead and add the current folder to the documents list, just so it'll get processed at some point. And then we go ahead and use our array spliterator technique. And if you remember what the array spliterator technique did, it goes ahead and makes an array spliterator. This is what's built in by default. And that'll go ahead and split this thing as an array. And then we null out the current folder and clear out the documents list because we just took care of that here. And then that spliterator is what gets returned. So you can see this implementation is substantially more complicated than the batch spliterator. And the jury's kind of out as to whether it actually runs any faster or not. I've tested it a bit. I think the main thing that would make this run faster is if you had large amounts of directories, subfolders, and documents. Then it would get a win. If you have largely small subfolders and with a small number of documents, you're probably better off with the batch spliterator because it's less overhead to do all the splitting. Okay, so that's what I wanted to talk about here today. Let's, for kicks, go over and see whether or not the GitHub is working yet. Maybe yes, maybe no. It doesn't look very promising. Nope, still not working. Oh, well. Well, what we're going to do tomorrow, just so you'll know, is tomorrow we're going to do the completable future version of this code, which is really, really cool. And it's entirely non-blocking and entirely recursive and entirely makes your mind melt. So we're going to walk through that one. And if I get inspired and can do an RX Java version, we'll take a shot at that one later in the week. But before we do that, let's see if there were some other questions. Let's see. Okay, so oh, I see. Yeah, we're just passing in this. So this is used when we work on the making the appropriate spliterator. So we have to make a spliterator for a given folder. So of course we have to pass in this. So that's fine. Is there a Pantheon account or a what is it account to support my efforts? No. I just do this to have fun. I'm at some point going to turn all this material I've been creating into slides that I'll use in my future versions of my courses at Vanderbilt and other places. Let's see. In the abstract file counter class, does the document count represent the count of docs inside the past arg? Okay, so this is a question that's left over from yesterday's stuff. So let's see. Let's go back. Go share our screen here, and we'll share this screen. And let's see if we can find yesterday's stuff, which is, let's see. Oh, I didn't, yesterday I didn't do, I used a different computer yesterday. Whoops, hold on. All right, this will take a second to bring up. So let me go ahead and bring up my IntelliJ, and let's go find the example that we're talking about, which was yesterday's folders, fork join, and build.gradle. So let's open that up. All right, so now let's go ahead and share the screen again, and we can see if we can answer the question. Whoops. There we go. Let's go ahead and share the screen. And there. So hopefully we'll now see file counter. And so let's go over here and find abstract file counter. All right, so now of course I've lost the the question. This is what I think was being asked. Let's see. Let me go back and find the question, because of course I've asked it. Okay, is the document count represent the kind of documents in? Oh, I see what you're saying. Yeah, good question. That's a great question. I wrestled with that particular issue when I did the design of this class, and what I ended up doing was the question is, could I have made these things static? And the answer is, I could have made them static, but then I would have had to have some API to reset them every time I wanted to rerun this program. Because of course, if it's static, it's shared by all instances of stuff. So what I ended up doing, if you take a look at the implementations that use this stuff, is I end up passing document count and M document count and M folder count. I end up passing those through, and they get stored at each level of the recursion. So it's not making a copy, just storing those things. And I did that intentionally so I wouldn't end up having to use static, which turns out to be kind of ugly, unfortunately. But yeah, that's a great question. I spent a lot of time wrestling about whether I should do that or not. Okay, so I think that's basically it for today's lesson. Tomorrow, as I said, we'll go and talk about the completable future version of this directory processing program, and I think you'll really like it. It's very, very cool and shows off the use of things like spliterators and collectors in the context of completable futures, which are really a kind of melt your mind sort of thing. So again, thank you guys so much for showing up, and I will look forward to talking to you again real soon.